All right, guys, I want to introduce the Iron Rain team. They're going to be talking about the introduction to gyros, which is a very important sensor that if you're going to be building robots, this is the first time you probably move beyond an encoder. So, very important step. These guys are hopefully going to make you all very knowledgeable in it, and they have used it in several of their robots. And if you look in the front here, you can see a balancing robot that has a gyro in it. I know that they have some other robots that use gyros. We're going to see that, and so to start off, this gentleman right here is going to, can you introduce yourself?
Yeah. Hi, I'm Jayesh. This is the Iron Ring team. We've been a robotics team for about 5 years, going to our 6th year now. Most of us are going into our junior and sophomore years, and today we'll give you a little introduction on gyros.
So it's not the Greek sandwich, right?
Okay, so I'm Caitlin, and the first gyro type we're going to be talking about is mechanical gyro. It has a flywheel, a massive flywheel in the center. It's spinning on its own spin axis, and this provides rotational inertia so that it's able to spin in a whole bunch of different directions, like in the top left diagram. So mechanical gyros, they can be used as sensors or to provide stability to any function that you really need. So in the top right, you can see this is the gyro in the Hubble. So a lot of orbiting satellites, they all use mechanical gyros, while in our robots we use just sensor gyros. They don't have that flywheel in the center, it's not spinning, and we'll be talking in more detail about how they work later on. But in the left, there are the low-cost MEMS gyros. These are the ones that use in the EV3, it's balancing over there. And the high-technic one, which is on a really large robot right there. Those are lower cost, and they're for lower accuracy. They have more drift than the higher-end gyros on the right, such as the ring laser, fiber optic, and the resonator. These are just different types, different technologies to do basically the same function overall.
So what is MEMS? So MEMS stands for, oh wait, I'm Tycho Moroni, sorry about that. So MEMS stands for Micro Electromechanical Systems, and they are very, very small mechanisms that have their own special microfabrication techniques. And they have a couple of different applications like gyros, accelerometers, microphones, stuff like that. But today we're going to be talking about gyros, accelerometers, and magnetometers. So accelerometers, they basically work by finding the location of a mass attached to some flexible plates. They detect the position of the mass relative to some fixed outer plates, and so yeah, they detect acceleration. So there's 1, 2, and 3 axis versions available, and there are a couple different ways you want to select your accelerometer, such as resolution, accuracy, and range. There are, of course, a couple ways to communicate with an accelerometer, like 2-wire interface and analog. That's it.
All right, so I'm going to talk about magnetometers. So what you want with the magnetometer is it's going to give you your position and your displacement depending on your on the magnetic field in that range as your object. So what it's going to help you do is adjust to magnetic north, and it's basically the same as accelerometers and gyros. It'll have your accessibility and your accuracy, but what it won't have is your range, because it'll have a limited range depending on Earth's magnetic field at that time.
I'm Max Ronnie. MEMS gyros work rather similarly to MEMS accelerometers. They use 2 masses, which vibrate constantly, to detect the instantaneous speed of rotation around a given axis. Like accelerometers, they usually come in versions with 1, 2, or 3 axes, and they have different interfaces like analog, TWI, and serial. And you'll generally want to choose among MEMS gyros for their range, resolution, their accuracy, and their stability.
So, hi, my name's Omar. How do these gyro things actually work? Like Max said, we have two test methods here, represented by large green box. And they oscillate, so they vibrate up and down, left and, well, in two opposite directions, keep that in mind. So, the Coriolis Effect, which is a weird, complicated thing that makes torque. So it creates torque perpendicular to the rotation of the gyro, and that's what the gyro senses using what are called capacitive combs, which are these really tiny micrometer scale combs. They basically mesh together. They don't touch, but they do like mesh together. And depending on how far they mesh, that's how the gyro can tell how far it's moved. And the test method vibrates in opposite directions, like I said, and that's to mitigate the effect of linear acceleration. So if, obviously in these robots, you're going to be moving around a lot like linearly, and you don't want any of those linear accelerations to be counted for in your gyro, because that's not what you want to be sensing with the gyro. For the gyro, you want to be sensing kind of other motion.
All right, so when you're talking about sensitivity, what you want is a range of rotation, and that just means how far the gyro oscillates. And what you're going to want in that sense is, of course, measured in degrees per second, is different gyros are going to be used for different situations. Meaning, let's say for a Wiimote, which has an accelerometer but not a gyro, that'll be in a separate attachment, but it's going to have a different range in sensibility than, let's say, you'll have in a mobile game. And you're going to want that for your devices. But here in robotics, the main range you'll see in the top left is going to be from 30 to 300 degrees per second, and that'll be in dead reckoning.
Okay, so all gyros have drift. The MEMS gyros, which we use, since they're the lower end ones, they have higher drift. They're not as accurate. So you need to calibrate your gyro often to be able to measure by how much is it off and take that number into account. So drift changes with temperature. If the temperature of your environment changes, you need to recalibrate because your previous number is off. So some gyros, they have built-in auto calibration that you can take advantage of. But basically, when you are calibrating, you're telling your gyro that you're staying still right now. You're going to have degrees per second of 0. But since your gyro is drifting a little, it's going to record a number that's a little off. So if you're recording 100 samples, with that example at the bottom, your gyro is not going to read exactly 0. So you're going to tally up by how much is it off, and then you can subtract that from future readings. That's how you calibrate. And integration, like I said, since your gyro is only recording the speed, the degrees per second, that's not really as helpful as your heading, because that's what you want. We'll be talking about a heading robot. You want to keep your heading, you want to turn exactly 90 degrees. That's really what you're looking for. So you want the displacement, your angular displacement. So integration is a way to go from acceleration to speed, or then speed to displacement. But in calculus class, you're going to be learning, like you learn all these rules and stuff that to memorize for functions, but gyros, you're not getting a function back, you're getting a whole bunch of samples. So at the very bottom, that's an example of a Riemann sum, and that's basically what your program is doing. So you're getting your previous displacement, and adding to that your corrected speed, because you get your raw reading and correct for it with your calibration, and then you multiply that by the time elapsed between your samples. So that's, distance equals speed times time. So that's basically what that function is. But the thing is, if your robot is not moving at a nice little function, it's not moving at a constant speed, so it's going to be off a little each time. You want to make sure that your time between each sample is short so that you don't get a lot of overlap or the little holes left in your function by the Riemann sum over there. But the thing is, if your samples are going too fast, then you're going to get a lot of built-up drift if your calibration is off a little bit or your temperature is changed. So you want to find a nice balance between taking accurate samples with a small amount of time in between and not like going crazy with drift, basically.
No calibration is completely perfect, and the drift will as I stated before, generally change with temperature and other kinds of things as well. So using techniques to compensate for drift is generally a good practice to help keep error low, especially since it gets amplified during integration. Recalibrating often, if possible, is generally a good way to keep the drift that builds up low. It's especially useful if the temperature is going to be changing often. For example, if it's going between different environments or if the robot itself heats up. A more simple strategy is to keep the use of the gyro low. So, for example, using the gyro, or rather putting the values you get from the gyro into integration only when you're doing something like turning, and when you're not turning, moving only in straight lines and keeping that heading using something like odometry. Generally, the best strategy is to use a complementary sensor in combination with the gyro to check for drift, to sort of cross-check for drift. So for a balanced robot like that one, the example would be an accelerometer, which should be used to detect the direction that gravity is pulling and cross-check that against your detected angle. And for a robot that uses a gyro for heading, like either of these two robots here, something else that would work would be a magnetometer, but that has some limits in that magnetometer is best to work outdoors and far away from things that emit electronic fields, like wires running through the floor, or even the motors in the robot. One way to simply remove all drift that's built up is to back into something like a wall that you know is there, and using that to sort of reset the known direction.
So when we talk about gyros, they operate in 6 degrees of freedom, like we have in real life. So if I can see that quadcopter right there. Well, that one, whichever. So the first 3 are translational axes, so left and right, up and down, and forward and backward. And then the other 3 are rotations around these axes. So first is yaw, also called heading or pan. That's turning like a car would. Next is pitch, also called elevation or tilt. That's basically your angle of attack. And the last is roll, which is basically your banking. So when we talk about the robots that we're using in this situation, in terms of coordinate system, what we really want to be looking at is the body frame of the robot. So the actual robot's thing, its own self, using either a gyro or an accelerometer. But if you're working with a drone or some other robot that is operating in the environment, like a car, then world coordinates are also useful, using a magnetometer, which is basically a compass, and accelerometers with gravity. Euler angles, quaternions, compass heading, those are complicated subjects that we're not completely versed in, but really what they are is that what they help you describe orientation, so where you're facing, where you're pointing. And finally, another option you can use is geocentric coordinates, so the Cartesian x, y, and z axes, latitude, longitude, those things. That can that's related to world coordinates, and they can help you determine where you are, location-wise.
So, you can see this balancing robot here. Most of you have probably seen or built one yourselves. So, a general misconception is that you have to have an accelerometer. That robot right there, it's actually a default kit that is provided with the NXT. It gives you instructions. And it has no accelerometer in it, and you can see it's bouncing just fine. The way it works is it takes its exponential moving average, which is how far it turns. So your robot it always has to overcorrect a little bit, so it doesn't fall backwards, and you can't actually stay at your top at the balance point, because generally something wants to knock you down, like wind or something. So you take how far you rotate around your 0, and you keep resetting that to 0 to counter your bias that is in your gyro. A case where this wouldn't work is, say, in a wind tunnel, or if you're moving 20 miles an hour, like on a car or something for some reason. So in that case, it's going to try to keep going forward to counter the wind, where it will just kind of eventually keep leaning forward, more forward, and once you stop, it'll just fall over, because it can't stay like there. It's not up. Although if you have an accelerometer, it might not correct hard enough, so it might also fall back. So that's kind of a problem. We haven't tested this yet. We don't have a wind tunnel. So, also, a use that you have for gyros is for turning. So it helps you keep your turn short and accurate. You turn until your target angle is reached. I have a robot here. It's going to turn 180 degrees. If it would work. Okay. Hang on a second. Maybe it's not this to happen.
So it's calibrating right now. It's taking
Yeah.
those 100 samples. It's calculating the drift. So it can do that
Just give it
accurate
a
180
moment.
degrees.
100's a big number.
Hopefully it works this time. Okay, there you go. It did a 180 degree turn there. So this might actually not be too useful on a robot with differential steering, because it can turn pretty easily if you know the diameter of your wheel. You can use odometry. But a case where this is more useful is on something with tank drive. Like you have one wheel on each corner that can't freely rotate like an omni wheel, where your robot's going to be bouncing around a lot, which in that case you can't rely on odometry. So that's one place where gyro turns are useful. So another thing that you can do with gyros is maintain a specific heading. You turn towards a target angle and you keep staying there. You turn like one wheel until you reach it. And you can pair this with PID to make it more accurate, because nobody likes to waggle. That's the worst way to do it. And you can also drive forward to basically follow an invisible line. So I have a couple robots here that can do that. This one, see if I turn it, now it just keeps turning back to the place it was facing when I started it. And to show that it scales, we have another robot here, if this one would work. So this one should also keep maintaining its heading. Very heavy. So,
Stay on this throwing range,
there you go.
Actually, it's set to throw in the directions.
Oh, it is? Okay.
Alright, so we talked about all these things, gyros, magnetometers, and accelerometers, but what you really want is to have these all together, because they all have their own errors, and you want them to help solve each other's errors. So, talking about IMUs and HRS, IMU inertial measurement unit, and HRS attitude dependent reference system, they come from the same basic technology, helping vehicles get specific data points and compounding that for that specific vehicle. The main difference between HRS and IMU is that an HRS has an internal unit that'll help you process some of that attitude data. Attitude meaning like altitude, just another way to say that. And of course, since it's based on that altitude, you're going to be using that a lot more in aviation. And then the IMUs in land and water vehicles, don't count me on that. It's just what we tend to see rather than what it actually is. So, of course, you're going to have onboard microcontrollers to give the user and whoever the pilot or driver is more usability in that sense. HRS is probably going to have a lot more few sensors, and that'll be explained in the next slide. So, as I said, what you really want is sensor fusion, because as an accelerometer, it'll help correct your error and drift 90 degrees off of gravity. The magnetometer will correct your yaw, it'll correct your yaw like compared to magnetic north, help you adjust to that magnetic north line. So what these devices help you do is it'll help you correct both the short-term error and the long-term, because as you correct both 90 degrees off from gravity and to magnetic north, it'll help your device stay on the specific heading you want it to go.
So where should you put all these devices on the robot? For example, in this small one, the gyros are on the back. Oh, hello. That larger robot, the gyro is on one of the right side, and on that balancer, the gyro is on one of the arms. So where, like, that doesn't make any sense. Where do you put it? For gyros, it doesn't matter. Assuming that you have a robot that has a fixed frame and nothing's like branching out and moving or anything. If you put the gyro on something that was out, then it might, because of all the shaking and things that might happen, it might experience different accelerations that would not accurately represent what the robot's really experiencing. For accelerometers, you want to put them near the center of mass of the robot, because that will give you a better average acceleration for the entire thing. Again, if you put it out on some limb, it's going to be swinging around a lot, like an actual arm does, and oh, don't mind it. If you put an accelerometer on the limb somewhere, it'll experience larger accelerations, most likely, and that's not what you want. And for magnetometers, you want to put them away from any other, well, mostly for that kind of robot, you want to put them away from any other electronics, for example, motors. Motors create magnetic fields, and that's going to mess up the readings. And you want to put them as high above on the ground, as high above from the ground as possible, like on some sort of mast. Because, well, if you're indoors, there are probably wires and things on the floor, and that will also mess things up. If you're outdoors, there's nature, there are no wires. So, well, there still are, but you probably are going to get a lot better readings. There isn't as much interference around.
So here are some lower cost IMUs. They're pretty accurate. We have some on these quadcopters actually. This is the Pololu one on the far left.
Right.
Right, okay. It's on the left. So, there you go. Those are some gyros that you can use. They are some IMUs.
Alright, so for smartphone IMUs, it's actually pretty recent that they started doing this. Most have 3 degrees of freedom, of course, on accelerometers and their magnetometers. The iPhone 4 was actually the first that mass-produced these in their devices. The Android, they have it only on their higher-end devices. You won't really find it on the lower end. Speaking on some specific brand names, even on the iPhone 6, they had a bad batch where it just completely, it didn't work at all. And they had to completely restart that. The Moto G 2nd Gen, I'll say it's erratic, but in truth it sucks. So the DTE speed, it has no gyro, so that'll eliminate a lot of virtual stuff you're going to do in that. And of course, sensitivity, as we talked about earlier, it'll be optimized for the handle.
So here are just some commands if you're developing an Android and you have a gyro or accelerometer that you want to use. There's some commands for you. That's basically all that's on that one.
You need a gyro.
And here's some other stuff for you to research if you want to learn more about this stuff. There's some other videos that explain stuff in more detail, like quaternions and things like that.
It was confusing. I recommend you not do that, but.
So,
Say more confusing than helpful.
Yeah.
You better learn it now. Let me tell you, when you're old, it doesn't get any easier. So learn
so
now.
that is all we have. Yeah.
We have robots
Some other
around here
robots to
that
show, I
if you
guess.
want to come look at and you can do that. If you have any questions, you can also ask those. Yeah.
So we have the Google Cardboard up here. It's an example of the smartphone IMU. It takes all the gyro and accelerometer readings, and you can play with the heading robots.
That one, you can't do much with that one.
That one died. Battery.
Yeah, thanks for that.
Thank you.
Okay. Thank you.